Okay, so welcome to Math341. This is lecture 7. And so what I want to do today is I want to talk about inclusion-exclusion bounds. I want to talk about derangements, talk a little bit about proofs by induction. Out of curiosity, how many of you have done proofs by induction? Oh, good. Okay, so I can't tell if that was a yes or if you have an itch. Okay. So most of you have seen proofs by induction, which is good. And then if there's time, I'm not sure if there will be, I want to start talking about PDFs and CDFs. And so again, there is far more material in both the book and in the course than we can cover in the lectures. So as you're reading the text, if there are things that you want me to go over in greater detail, please let me know. And we can either do it in the class proper, we can do it in office hours, we can do it with the TAs. Otherwise, what I'm going to do is I'm going to try to choose items that I think have a nice story to tell that illustrate a really good point. All right, so as I said, we'll be talking about inclusion-exclusion bounds at first. We mentioned that beautiful formula before where the probability of a union was the probability of the events minus the probability of the intersections of pairs plus the probability of the unions of the triples and so on and so on and so on. And what's nice is if you stop it after you've just done something with a plus sign, that's going to be an upper bound for the probability. If you stop it after a minus sign, it's going to be a lower bound. So sometimes for difficult problems, you don't necessarily need to know the exact answer. You just need to know fairly close. In pure mathematics, there are some wonderful situations where you know something is an integer. Well, that's great. If I know it's 9.99999999997 plus or minus a little bit, it's got to be 10. And so sometimes just getting close is more than enough. A derangement is when you take the numbers 1 through n and you reorder them and no number returns to where it started. And so one of the more natural questions to ask is, what's the probability if I randomly permute the numbers, I return a derangement where nothing moves back to where it started? And it turns out that there are interesting and important applications of this. All right, if there is time, I want to talk about some tricks for multivariable calculus and just the ability of rescaling things. Right, so let's do an inclusion-exclusion example. So this is a problem from Bridge. So again, we have a deck of 52 cards, 4 suits, and I want to calculate the probability that at least one person has all their cards in one suit. Cool. So can somebody tell me what's the probability that a specific person has all the cards in one suit? So, probability. So probability north is 1 suited. So how can you make sure that one person has only cards from one suit? How many ways can we do that? So there's 4 possibilities. And then how many ways can you give them 13 cards? 52 choose 13. So it's 4 divided by 52 choose 13. Another way of looking at it is there's 4 choose 1 ways of choosing a suit. Now that I've chosen a suit, let's say I've chosen spades, how many ways are there to give them all 13 spades? So they've got to get all 13 spades. How many ways can you give them all 13 spades? I'm sorry? No, there's 4 ways to choose which suit. The 4 choose 1 is I have 4 suits and I choose one of the 4 suits. So let's say I chose spades. Now I have to give them all 13 spades. I'm sorry, 1 way. But how would we say 1? We would say 1 is... It is 1, but in terms of choosing, they've got to get all 13 spades. So how would you do that with a choosing? There's 13 spades, and I choose 13 of them. Now, how many cards are left? 39. And so I have to choose 13 cards for the next person. 39 choose 13. Now there's 26 cards. I choose 13 for the next person. And now this would be the same as how many ways can I divide? How many ways can I create hands. So that would just be 52 choose 13, 39 choose 13, 26 choose 13, 13 choose 13. And you can see when I write it like this, that there's going to be tremendous cancellation. And these expressions will be equal. That's the probability that north is one suited. What's the probability that south is one suited? Same. So what is the probability that at least one person is four suited? So we know the probability that one person is one suited is 4 over 52 choose 13. What's the probability that someone, see, this is the special person north. What's the probability that someone is one suited? Why 16? So why are you doing it times 4? Okay, so 1 could say is equal to 4 times probability north is one suited. Is that correct? So we're double counting 2 people being one suited, right? And if we're double counting 2 people being one suited, what's the next danger? 3 people. Now, what's interesting is if 3 people are one suited, what do you know about the 4th person? They're also one suited. So this is not quite right. So this is minus something small, right? Let's try to get a sense of how small we are. So if we just did 4 times the probability, we would be wrong. I will give a tremendous amount of extra credit to anybody who can write a computer simulation that can detect the difference in these probabilities by brute force simulation. Okay? So the answer is not 4 times the probability that one person, it's a little bit off from that. That's an upper bound, it's a little bit smaller. If you can write a computer code that can do enough calculations, let's try to get a sense of just how difficult this would be. So 52 choose 13, that was the denominator. That's about 6.35 times 10 to the 11. A million is 10 to the 6, billion, 10 to the 9, trillion, 10 to the 12. The denominator is almost a trillion. So what we're saying is every trillion hands, you expect to see it a few times. So you have to write code that can handle on the order of 10 to the 11 simulations. Can you do that? Can you do that on a laptop? So you need to have some idea of what is your computer capability. You know, is this something that you can expect to be able to do? So I wrote a really stupid program. I just count from 1 to a specific number. I don't do anything. I just count. And I do, how many times do I do it? Binomial 4n choose n. So if n is 13, that's 52 choose 13. So when I took n equals 10, I was counting up to 40 choose 10. That took about 3.4 seconds. When I did 11, it took about 34 seconds. I'm sorry, this was 8. Sorry, this was 8. Sorry, this was 8. This was 9. So this was 10. So 10, that's 40 choose 10. That took on my dinky laptop 346 seconds. Anybody know roughly how long that is? Ballpark. About 6 minutes. These seem to be going up by approximately an order of magnitude, roughly from where we are. So to get up to 13, I would need another 3 of them. From 6 minutes, multiply by 1,000. Is that doable? To get from 6 minutes to an hour, what's that? That's a factor of 10, right? So we're talking about 100 hours. Is 100 hours reasonable? I'm sorry?
Not for your laptop, but
For my laptop can do $100. I could probably give everybody in this classroom right now a laptop from some point in my career. I've got a collection of them. Now, the older ones are really not worth much nowadays, but I have some laptops that are not that old. I could have it running, and I've done this for some of the research I've done with students. I've had laptops run for a couple of days in my office. 100 hours, I'm not thrilled, but I can do 100 hours. That's not so bad. But the next level, to see the difference in probability, with enough simulation, if I let this run maybe for a week or a month, I think I could see the probability pretty accurately. The event is rare, but not so rare that my computers can't do it. But to see the difference in probability, no, I am not going to be able to see that. So I will give extra credit to anybody who can write a code and do enough calculations. You're going to have to paralyze, basically get a lot of friends enslaving their computers to do that, to see that small difference in probability. All right, so we've talked a little bit at the end of the last class on the law of total probability. And so we talked a little bit about what it means to partition a space. So if I have the set of all possibilities omega, what I want to do is I want to break omega into different subsets. And these subsets are disjoint, and their union should be all of omega. So maybe this is B1, B2, B3, B4, and B5. And so we write omega is equal to, like this, B, I'll say I goes from 1 in this case to 5. And when I write the union sign like that, that means disjoint union. Okay, so if I give you some event A, and I want to calculate what's the probability that A happens, I can break this up into a lot of simpler calculations. Let's assume B1 happens. What's the probability that A happens given that B1 happens? And then multiply that by the probability that B1 happens. And then we look at, well, what happens if B2 happens? What's the probability that A happens if B2 happens? And then multiply that by the probability B2 happens. What would be the easiest event A to calculate the probability of? I'll accept 2 answers. Easiest event to calculate the probability that it happens. When in doubt, there's always 2 events that should be really easy to calculate. Be a wise ass. The empty set or everything, right? So if I take A to be everything, the probability that something happens is 1. And if you look at what happens on the right-hand side, all of the conditional probabilities would become 1, and I would get the sum of the bn's equals 1. Okay, that's what should happen if I have a partition. The sum of the probabilities of the b's should be 1. So we get the sum of the probability of the bi's equals 1. And I did a partition here into 5 pieces. Any finite number of pieces would be fine. Any countable number of pieces would be fine. And this is where it's a first course in probability. I'm not going to go into countable versus uncountable. Think of it as long as I can index my events B1, B2, B3, Bn, where n ranges over the integers, that's fine. We can't do things where we have it ranging over the real numbers. We're not doing uncountable number of pieces. So this is a really useful expression if we can calculate the items on the right-hand side. If I can calculate the probability that each B happens, and if I can calculate the conditional probabilities, I can then use this to calculate the probability of A. Think of this as breaking things up into cases. If you try to prove something, if you try to calculate something, it's in general very hard to do it because you don't have a lot at your disposal. Let's break it up into cases. In this case, let's assume the following happens. Now I have this stuff to play with, and hopefully the calculation becomes easier. And then maybe I'm in another case now where something else happens and I can use that. And that's the idea, is you want to break probabilities up into different events where they're going to be easier to calculate. And so over here, this is another way of writing Bayesian. The probability that A happens given B is the probability B happens given A times the probability of A divided by the sum of the probability that B happens given AI times the probability of AI. Oops. And there's a typo here. The denominator is not the probability of B. What is the denominator? Oh, no, it is the probability of B. Sorry, yes, it is the probability of B. Yes. Because I'm having the A's range over a partition. So I switch now the A's of the partition space. So this is just a fancy way of writing the probability of B. I could just write the probability of B down below if I have that. So it all comes down to what events do you have? What events are easy to compute? And so before we get to derangements, I want to say something very brief about language. Language is extremely important in mathematics. People often are informal. My father got into trouble many years ago, and my mother came up to him very upset because they were at a party, and he said that, did you know that my wife has a son in college from her first marriage? You're implying that she was kind of old. And what else do you think might be true if my father says that she has a son in college from her first marriage? Yeah, that she's on her at least her second marriage. No, she'd only been married to my dad. He'd only been married to my mom. I was actually proud that an engineer would do something like that and use language like that. And so the implication when you used a phrase like that was, she has been married at least twice. Doesn't mean that. All it means is she's been married at least once. So one of the big things in mathematics is there is a difference between exactly and at least. If I say something happens exactly k times, it doesn't happen k minus 1 times, it doesn't happen k plus 1 times, it happens k times. Sometimes we'll say something happens at least k times. It could happen 0 times, 1 time, 2 times, any number up to k times. And it turns out we can often go very easily from one to another. Imagine I know how to calculate the probability that something happens at least so many times. If I want to figure out the probability that it happens exactly 5 times, we'll just figure out the probability it happens at least 5 times, figure out the probability it happens at least 6 times, and subtract. And this game, when you subtract, you remove all the ones that happened when it's at least 6 times. Oh, I think I might have gone the other way. I think I was saying at most a moment ago. My apologies. I'm doing at least. So if I say it happens at least k times, it happens at least k times means it happens either k times or k plus 1 or k plus 2 or k plus 3, etc., etc., etc. So if I want to know the probability it happens at least 5 times, just look at the probability it happens 5, 6, 7, 8, 9, etc. Subtract from that the probability it happens 6, 7, 8, 9, etc. And that will leave you with exactly. So I can go very easily from at least to exactly. What about the other way? What if I know the probability that something happens exactly? Well, if I now want to calculate the probability that happens at least k times, just do the probability it happens exactly k times, plus the probability it happens exactly k plus 1 times, plus the probability it happens k plus 2 times, and so on and so on and so on. So one of the big themes from this course is, depending on how you have information, sometimes one approach is easier to use than another. And just be aware that depending on what you have, one might be better. Be alert. We'll see stuff like this again when we go from the PDF to the CDF. All right, so the next one is just counting derangements. So a derangement is everything moves. So I take the numbers 1 through n, one, two, dot, 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 n, and I reorder to, let's say, k1, k2, dot, 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 kn, and require that KL does not equal L. Anybody here take abstract algebra? And for the record, I will have to say my hand is also not up. I have never taken abstract algebra. That's a long story. So in abstract algebra, you often talk about permutations. And you look at permutation groups and whatnot. This is a big topic. One of the reasons we care so much about this is this allows us to construct efficient graph networks. So imagine I have, 1, 2, 3, 4, dot, 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 n minus 1 and n. And then this is going to be what's called a bipartite graph. and only stuff from above goes to stuff below, and only stuff from below goes to stuff from above. So there's no connections between the vertices down below with each other. There's no connections with vertices above with each other. And what I want to do is I want to create a graph. I'm going to create a deregular. I'll do a two regular graph. So each vertex has two edges from it. And so the simplest thing is I can always change my labeling. So the very first time I just send 1 to 1, 2 to 2, 3 to 3. And now what I can do is I can now make another set of connections. And maybe this time, maybe this time, didn't change color. So maybe this time now 1 goes to 2, 2 goes to 1, 3 maybe goes to 3, 4 goes down to here, maybe something like this. And in a situation like this would not be a derangement for the second connection because I'm sending 3 back to 3. For the first one, I don't really care because I can always reorder the bottom. So 1 goes to 1, 2 goes to 2 for the first time. But for the second time, I don't want something like this. Why would this be bad? Why would you not want a graph like this? So think of the edges as allowing different vertices to communicate with each other.
Anyone that ends up in the same spot is isolated.
So right now, I've actually isolated 3 from each other. Now notice that 1 and 2 are also isolated. For small numbers of connections, you expect to have some isolation. So isolation, that's bad, but there's another reason why this is a bad choice. And most people don't seem to understand this, but I will remind you, resources are limited. You do not have unlimited wealth. Again, as always, if I'm wrong and you have unlimited wealth, please see me after class. Or in fact, see me right now. I will cancel the rest of class. What's bad about something like this, given that we don't have unlimited wealth? What did we just do? We already have a path from 3 to 3. So if we only have finite resources, why are we connecting 3 and 3 again? There's probably better things to do. Now, it could be that this might be an extremely important connection. We might need to have a backup. We need to make damn sure that they can communicate. So it might be worth doing something like this. But it turns out you can construct graphs that have remarkable connectivity properties by doing stuff like this. And this is a huge industry trying to use the fewest number of vertices to be able to quickly have any vertex reach any vertex. If I want to use a lot of vertices, we'll just connect everything with everything. But it's not a challenge. How long would it take any vertex to communicate with any other vertex if everybody's connected to everybody? 1 step. But it would be very expensive. You have n vertices. If I want to connect everything to everything, that's n choose 2. There's n choose 2 pairs. That's on the order of n squared. It turns out if you do a d-regular graph so that every vertex has exactly d neighbors, that's linear in the number of vertices. And if that can have good connected properties, 3 steps is often not so bad. There's a lot of really good videos about the undersea cables. And there are certain parts in the Pacific where when the cable breaks down, it's a real issue in terms of routing calls and internet to them. So there's a reason why we care about stuff like derangements. Trying to figure out, if I just choose a permutation at random, what's the probability that it would be valid? If it's a high probability, then I might be able to construct some of these graphs very quickly, and maybe a random graph is going to have some good connectivity properties. And so I want to calculate what is the probability that I have a derangement. So this gets hard, right? If I want to calculate the probability of a derangement, so how many spots, how many things do I have for the first spot? So I want a derangement. How many things can I put in for the first spot? n minus 1. So I have n minus 1 choices for the first spot. Because if it's a derangement, it can't be a 1. How many choices do I have for the second one? Why n minus 2?
Only had n minus 1 remaining, you can't put 2 in spots.
But what if I put 2 in the first spot? Then everything works. So it's n minus 1 or n minus 2. So it's n minus 1 if 2 is in the first spot, else it's n minus 2. I hope this is enough to show you that we don't want to solve the problem this way. What kind of probabilities would these be? Dependent conditional probabilities. The number of options I have for the second box depends on what goes in the first box. And you can just see the nightmare coming, right? By the time we get to the third, fourth, fifth, oh my Lord, which ones are still free? Which ones have been used? Well, it really just matters when I'm at 3, have I used 3 in either the first or the second? And just keeping track of all that is really painful. So we want another way. So instead of calculating the probability of a derangement, what might be an easier thing to calculate? So what's your definition of an arrangement? So does everything go back to where it started? Okay, so in that case, how many arrangements will there be? If the arrangement means 1 goes to 1, 2 goes to 2, 3 goes to 3, how many arrangements are there? There's only 1. So you're on the right track. Arrangement is too strong. So derangement is nothing goes back. Your arrangement is everything goes back. Can you give me some kind of balance between those extremes?
There's just like a probability that at least 1 goes back to their spot.
Not at least 1. Instead of at least, instead of at most, only 1 word is left. Exactly. Right? So these are the possibilities. We could do maybe at least 1 is fixed. At most, 1 is fixed. Exactly 1 is fixed. So those are good suggestions. And these kind of balance the extreme cases of nothing versus everything. So the question is, which event do you think is going to be easy to calculate? So if we want to calculate at least 1 is fixed, I could have 1 fixed or 2 fixed or 3 fixed. That's going to be painful. If I wanted at most 1 is fixed, so
yeah, just then we end up with the previous problem where none of them are
right.
Or
So we need to modify. Do for a specific number or spot. So let a k be the event k is fixed. And we don't care about anything else. So I only care about the element k is fixed. So the probability of A1 equals the probability of A2 equals ... equals the probability of AN. All of them are going to be the same. Right? So I don't care about anything else. I only care about is the first element fixed. So if the first element is fixed, how many choices do I have for the first spot? 1. And now I have n minus 1 boxes left over, and I have n minus 1 numbers. How many ways can I put those n minus 1 numbers into those n minus 1 boxes? N minus 1 factorial. And how many ways can I arrange the n numbers? How many permutations do I have? That's just n factorial. So it's just 1 over n. Let's let probability of A12, that's going to be the probability of A13 equals ... equals probability an minus 1n. What do you think the event A12 is?
Both 1 and 2.
So 1 and 2 are fixed. 1 and 2 fixed. Do not care about the rest. So what's the probability that 1 and 2 are fixed? How many choices do I have for the first box? Just have 1. How many choices would I have for the second box? I would also just have 1. And now I would have n minus 2 factorial ways to put everything in the remaining. Divide by n factorial, it's 1 over n minus 1. So is the pattern clear? So it always comes down to what event is easy to calculate. And here, if I tell you, I only care about specific numbers, I can calculate the probabilities that those numbers are fixed. Now, is it possible that 1 and 2 are fixed and 2 and 3 are fixed? Yeah. And in fact, if 1 and 2 are fixed, it's a little bit more likely that 2 and 3 are also fixed, because you know 2 is already fixed and you know 1 is not available to go to 3. Okay. So now we do inclusion-exclusion. So let's look at the probability A1 union A2 union ... union AN. This is the probability that something is fixed, right? So this would be the sum of the probabilities that the first element is fixed, the second element is fixed, etc. Then I have to subtract, so we'll just sum I1 equals 1 to n minus the sum 1 less than equal to I1 less than I2 less than equal to n of the probability AI1 I2 plus ... So is the pattern clear? So for the first one, what's the probability that one element is fixed? We just said that that was 1 over n. And how many ways are there to have one element fixed? There's n. So it's going to be n times 1 over n. Now for the next one, how many ways are there to choose 2 distinct indices from 1 to n? N choose 2. And so now we have minus n choose 2. And each one of these we showed a moment ago was 1 over n minus 1. The next one is going to be plus n choose 3, 1 over n minus 1, n minus 2. And we have to figure out, is it a plus sign or a minus sign at the end? Okay, well, when it was even, it was a minus sign. When it was odd, it was a plus sign. So this should be -1 to the either n minus 1 or n plus 1. I'll do n minus 1. Doesn't really matter. So that's the formula. Now, what's n choose 2? That's n times n minus 1 over 2 factorial. So this is going to be 1 minus n minus 1 over 2 factorial n minus 1 plus n minus 1 n minus 2 over 3 factorial n minus 1 n minus 2 plus dot 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 plus negative 1 to the n minus 1, and then we'll just have n factorial over n factorial. And so notice it just becomes 1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial plus dot 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 plus negative 1 to the n minus 1. Oh, sorry. There's an extra n factorial in the denominator, sorry. Because let's say 0 factorial, n factorial, and the last one is just 1 over n factorial. And now this is where we just have to do a little bit of manipulation to try to recognize what this is. Does anybody recognize this number? It's close to a special number. It's close to E, it's not quite E. How should I view the 1? We have a minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial. How should we view that 1? Yeah, this should really be a 1 over 1 factorial. And well, if we have a 1 over 1 factorial, what term do you think we're missing? So we should have, well, not 0. Everything else has 1 as a numerator. So there should be a minus 1 over 0 factorial. So we have to put in a 1 over 0 factorial over here. Well, 1 over 0 factorial, that's just 1. So this is the same as 1 minus, then I can pull out the minus sign. And it's 1 over 0 factorial plus 1 over 1 factorial. Sorry. Should be minus 1 over 1 factorial. Plus 1 over 2 factorial minus 1 over 3 factorial plus dot dot dot, and then plus negative 1 to the n 1 over n factorial. And this is approximately 1 minus e to the negative 1, as e to the x is the sum, m goes from 0 to infinity, x to the m over m factorial. So this really looks a lot like just e to the negative 1. Whenever you do a calculation, you always ask, is this reasonable? This is supposed to be a probability. What can you tell me about probabilities? Between 0 and 1. This is between 0 and 1. That's reasonable. What's really nice is we wanted the probability of a derangement. This is 1 minus the probability of a derangement. So life is really good. And so this implies probability of a derangement converges to 1 over e as n goes to infinity. If you want the exact answer, it would be that finite sum up to n. That would be the probability of a derangement with n terms. As n gets larger and larger and larger, it's going to converge. Because the exponential function grows so rapidly, it's going to converge very quickly. So I did some simulations at home. It's a pretty straightforward program to write. And then I did 10 million trials with n equals 5. The theory is 36.667, the limit is 36.78, and I observed 36.678. So what I was observing numerically, just what fraction of the time do I have a derangement, was really close to the predicted value. And it was close, but it was not perfect with the limit as n goes to infinity. So 5 is not infinity. If I took 20, however, you can see there's almost no difference between theory and the finite truncation. To 4 decimal places, I'm not seeing the difference. How many of you have taken a stats class? Okay, and when Moses came down from Mount Sinai with the laws of statistical comparison tests. What value of n is sufficient? If you want to use like the central limit there, they typically say if n is what, are you okay? Yeah, as long as n is 30, you're fine. I can come up with a strange distribution where 30 won't work, but for most of the stuff you use, 30 is fine. Here at 20, it's already almost perfect. And so it's a nice exercise, try to figure out what's a nice way to write code to calculate, a derangement. What's a nice way to write code to calculate the probability that somebody has all their cards in one suit. And, depending on what you're doing, I'll just make one quick announcement on coding. Has everybody here done a Sudoku? So how do you tell if a Sudoku is correctly solved? What do you have to do?
Check out the rows, columns.
Good. So how do you check to see if a row is correct?
Make sure every number 1 through 9.
Make sure every number 1 through 9 occurs. Okay, then you do that for every column, then you do it for every block. That's a lot. I can check all the rows with one check. I'm going to use for Sudoku 1, 10, 100, 1,000, ... and see if it sums to 111, 111, 111. So if I do it like that, the only way I can get a sum of 111,111,111 is if the row has exactly 1, exactly 110, exactly 100. This is a nice, fast way to code. You can do a similar trick with the suits. And so maybe you can do something like that. So you can sum the values of hands and see, do any of the 4 hands sum to something specific? Do you need to sum all 4 hands? Why not? Yeah, if you know the sum of 3 hands, you immediately know the sum of the 4th. Most of the time, your computers are so good and the problem you're doing is so minor, it doesn't really matter to be this efficient. But it's just worth putting this out there for you to always think about, how can I make my code efficient? If I know 3 of the sums, I know the 4th. It's forced on me. So just always be thinking, what can I do? What can I trim? So as an exercise, try to see, I'll give a tremendous amount of extra credit if you can write a code that can distinguish between one person and more than one person getting a 1-suited hand. The probability of 2 people getting a 2-suited hand is so small. It's just, I don't think you can write a good enough code with the computer power you have available to see this. My probability textbook when I was an undergraduate talked about perfect deals where everybody was 1-suited. How likely is this? Do you think this is likely at all? Should this be observed between the dawn of time and now? So I encourage you, do the calculation. Calculate how many ways there are to deal out a deck, where order doesn't matter which cards you get, just which 13 cards do you get. And the book made the wonderful remark that amazingly, while there had been numerous reports of perfect deals, nobody reported a semi-perfect deal where exactly 2 people had all cards in a suit. That was never reported, but there were multiple reports of everybody being dealt a 1-suited hand. What would you conclude when you're getting all these reports of 1-suited hands? They're false or poor shuffling, or actually maybe really good shuffling to make that happen, right? So, if it just look at things in comparison. Why are we getting all these reports of perfect deals and no reports of semi-perfect deals? I can see why we're not getting any reports of exactly 3 people being dealt a 1-suited hand, because as soon as you get that, you get the 4th. Okay. The next is multinomial coefficients. I want to just talk briefly about these. Depending on where you go, these are great generalizations. as always, whenever you see something new in math, you always want to return to something you already know. So Mississippi, oops, sorry. I was going to say Mississippi is a hard word to spell, but if I'm writing it down, it's actually not that hard to spell. Can anybody spell it? Yes.
MISSISSIPPI.
Nope, it's IT. Language matters. I said Mississippi is a hard word. Can you spell it? But yes, this is old joke. So this is Mississippi. All right. Massachusetts is not a good state. Can somebody give me what they think might be a good state? I like Ohio, but Ohio's not a good state. Technically, New York would work. It does have a space in it, so can we remove the space? So what's the difference between Mississippi and New York when you look at these letters? Repeats. So repeats makes things much harder. How many ways can you reorder the letters of New York if you want to use all the letters? Seven factorial. So we have 7 factorial distinct words. Almost none of them will actually be real English words, but we can reorder them. What about Mississippi? So if you want to reorder something like Mississippi, it's much harder because I've got multiple S's. And so if I just change the order of the S's, it's still going to be the same word. So what we do is we put on some subscripts and then we forget them. So let's call it I1, I2, I3, I4, S1, S2, S3, S4, and then P1, P2. And just so M doesn't feel all alone, we'll give M a subscript of 1. So now we have 11 distinct letters. We'll count S1 different than S2. So now, how many ways can we reorder these letters? Well, now we have an index. It's 11 factorial. And now what we're going to do is we're going to forget about the indices. So we have 4 S's. How many ways? So there's got to be 4 spots in the 11 that have an S. So maybe we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Maybe we chose S's go here, 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 and here. How many ways can I order where those 4 S's go? Well, I'm choosing these 4 spots right now. I'm saying these 4 spots are going to have an S. And so initially, maybe it's S1, S3, S4, S2. But it could have been S2, S4, S1, S3. How many ways can I choose what order to put the 4 S's in those 4 fixed spots? 4 factorial. So I would take my 11 factorial and I would divide by the 4 factorial because there are 4 S's. And then similarly, I would divide by 4 factorial because there are 4 I's. I would divide by 2 factorial because there are 2 P's. And then I would divide by 1 factorial because there's 1 M. And I do want to write the 1 factorial. What do you notice about 4, 4, 2, and 1? They add up to 11. So I could actually revisit this 7 factorial. How could I view that 7 factorial? It's 7 factorial over 1 factorial, 1 factorial. Oh, this is going to be terrible in terms of writing. 1 factorial times 1 factorial times 1 factorial dot, 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 times 1 factorial. Right? I could view the 7 factorial like that. And so if I do like this, these now become the multinomial coefficients. And so if I give you n and I give you, say, k1, k2, ... kl, where 0 less than equal to k1, k2, ... kl less than equal to n, and k1 plus k2 plus ... plus kl equals n. So these are the multinomial coefficients. And not surprisingly, like the binomial coefficients, they have an interpretation. Now, remember, if I give you something like, n choose k, can somebody give me a combinatorial story? What does n choose k mean? Good. And so I can view this as n choose k times n minus k choose n minus k. Normally, we would never write the second factor. Why won't we write the second factor? It's just one. The problem is when we start dropping those factors, it becomes harder to understand and follow what's going on. It's useful to have stuff like that. And we get these by expanding things out, x plus y to the n, and that's going to be the sum. K goes from 0 to n, n choose k, x to the k, y to the n minus k. How do you think I might get multinomial coefficients? Where do you think multinomial coefficients might come from? So binomial coefficients came from expanding x plus y to the n. What do you think a trinomial coefficient might come from expanding? Yeah, x plus y plus z. And if we look at it, if I take n choose k n minus k, that would be a multinomial coefficient where I have two things that sum to n, right? This would be n factorial over k factorial n minus k factorial. That's what our multinomial formula tells us. Oh, that's just the binomial coefficient n choose k. So it reduces or you could say it recovers. Either one of them is fine. So really, if I look at the multinomial coefficient with just two items, I'm just regaining the binomial coefficient. And so if you expand out x plus y plus z, you will get multinomial coefficients with three things. If you do w plus x plus y plus z, you'll get things with four. Now, there's a lot of ways you could do stuff like this. Let's say I want to calculate x plus y plus z to the n. Anybody know a good way to expand this? So mathematicians are lazy. You always want to reduce something to a previously solved problem. Have I told you the joke of the mathematician and the engineer walking down the street? So they see a house on fire, and in front of the house there is a hydrant with a hose disconnected. So the mathematician quickly connects the hose to the hydrant, turns it on, and puts out the fire. They keep walking, and they see a house perfectly fine with the hose connected to a hydrant. So the mathematician disconnects the hose and sets the house on fire, thereby reducing this to a previously solved problem, and just keeps walking down the street while the engineer stares at him in disgust. It's worth remembering this. You should not reduce things to a bad problem, but whenever possible, try to reduce things to a good situation. The mathematician was trying to be good. It's like, I know how to solve this situation. Whatever you give me, I'm going to manipulate it. I'm going to move it to a situation I know how to deal with. I know how to deal with the case of a house on fire with a disconnected hose by a hydrant. You may not want to move to that case, but she knows what to do in that case. Do you know the formula to expand x plus y plus z to the n? No. What do you know that's close to this? So how can I use the binomial theorem with this? Yeah, let's group. So I can write this as x plus y plus z to the n. And now this would be the sum. Let's say k goes from 0 to n of n choose k, x plus y to the k, z to the n minus k. And now what can I do with x plus y to the k? What can I use to attack that? Yeah, binomial theorem. So then this would be the sum k goes from 0 to n, n choose k, and I would have a sum maybe L goes from 0 to k of k choose L, x to the L, y to the k minus L, z to the n minus k. So this is the sum k goes from 0 to n, the sum L goes from 0 to k, n choose k, k choose L, x to the L, y to the k minus L, z to the n minus k. This is looking a lot like a multinomial coefficient. But with a multinomial coefficient, I'm supposed to have three things. But if you think about it, when we looked at our definition for the multinomial coefficient, I have, say, L objects, they have to sum to n. Once I tell you L minus one of them, do you know what the last one is? If I have three numbers that sum to 100 and the first two sum to 90, what's the third? It's 10. There's no freedom. So even though it looks like I have L variables here, I only have L minus one free variables. Once those are determined, the last one is forced. It's actually quite reasonable that I only have a double sum here, not a triple sum. Because once I fix two of the indices, the third is fixed. All right, let's analyze this quantity. This is n factorial over k factorial, n minus k factorial. Oh, did I make a mistake? No, this is okay, this is fine. And then over here, I have k factorial over L factorial, k minus L factorial. When you look at this, what do you notice? Yeah, so the k's cancel. And we're left with n factorial over L factorial, k minus L factorial, n minus k factorial, or the multinomial coefficient n choose L, k minus L, n minus k. Okay. There's the multinomial formula. I just did it in this special case when we had three things. The same argument works. Lather, rinse, repeat. If you have four things, you can group three of them together, and then you have to just prove a couple of identities about multinomial coefficients. But if you think about what's happening is if we expand, we've got to have some number of powers of x, we have to have some number of powers of y, we have to have some number of powers of z. The sum of the powers has to be n. And so I'm choosing exactly L of them to be x's, exactly k minus L to be y, and then I'm forced to have n minus k to be z. And when I look at all the ways I can do this, well, it doesn't matter which ones I choose. It just matters how many ways can I choose. Yeah. All right, so you have to write it up carefully, but this is just a natural generalization of binomial coefficients. And when you're doing these choosing problems, there's a lot that you can do. All right, so I'm going to end the combinatorial part of the course with one of my favorite combinatorial problems. And so the image on the right is from the National Bobblehead Hall of Fame and Museum. And yes, there really is a National Bobblehead Hall of Fame Museum. All right, so this is one of my favorite problems. When I was a postdoc at Brown, there was a free food email list maintained by the grad students. And they would send out emails saying at 4 o'clock today in this room, there will be a talk on this subject, and here's the food. And the grad students would decide whether or not the food was worth it. Oh, you're serving pizza? I'll bring my grading. I'll sit in the back. Yeah, I'll do that for pizza. You're giving us vegetables? No, thanks. I'm not going to come for vegetables. And so there were free food meal lists. Here is a related food problem. We have C cookies that are all identical. And we have P people that we'll assume are distinct. Sadly, it is not always the case that professors consider students distinct. Sometimes they consider them just interchangeable slaves, especially in certain labs. But we will assume the graduate students are distinct. We will assume the cookies are identical. It doesn't matter which cookies you get. All that matters is how many cookies do you get. And so the question is, how many ways to divide all the cookies among the P people? So again, all that matters is how many cookies a specific person gets, not which cookie. Can somebody give me a painful way to do this? It doesn't have to be something that you would want to do. Let's say C equals 10 and P equals 5. How could we solve this? And we'll give the graduate students the wonderful names A, B, C, D, and E. Can somebody give me one solution? Yeah. What's the next solution? That's 1 is to do 9, but there's another solution that I think is more natural than A gets 9. B gets 10. So how many ways are there to flip these around? 5. So I'm going to put a 5 over here in parentheses and say that there's 5 ways to rearrange this. Now let's do your suggestion of A gets 9, and then what happens next? How many ways are there to rearrange those? 5 times 4 is 20. It's not clear yet what's the right pattern to view this. Do you think the pattern involves factorials? Yeah, we're talking about arranging things. What's next after the 9, 1? 8 and 2. And this isn't so bad. That's also going to be 20. What's next? Yeah, now things get interesting. How many ways are there to do this? So the claim is 5 times 4 choose 2. Let me get rid of all the parentheses. Why is it 5 times 4 choose 2?
I was thinking 5 gets 8, and then there are 4 spots for 8.
Does that seem reasonable? If you're not convinced, what you can do is you can go through and you can enumerate every possibility and see if it works. If this were to be a multinomial coefficient, what would the top be for the multinomial coefficient? What's the only possibility for the top for any of these multinomial coefficients? How many people do we have? We have 5 people. So the top should be a 5. So maybe as a multinomial coefficient, it's 5 factorial. how could I view the 81100? I want to view this as 1 factorial, 2 factorial, 2 factorial. So 4 choose 2 is the same as 4 times 3 over 2 times 1, which is 3 times 2, which is 6 times 5 is 30. And then 5 factorial over 2 factorial is 5 times 4 times 3 divided by 2 is 5 times 2 times 3, which is also 30. So maybe the number of weightings is related to these multinomial coefficients. Because if you think about it, C, D, and E, I don't really care which one gets the 0. So if I tried to do this with a multinomial coefficient, that maybe is 5 factorial over 1 factorial, 1 factorial, 3 factorial, which is 5 times 4, which is 20. So maybe I can actually get these by multinomial coefficients. And then I just have to look at all the different ways of doing this. Have fun. Right? You can do it, and again, how would you do this? I would write a computer program and just have the computer go through and enumerate all the possibilities. For a while on Google, I had the #1 hit for Math Riddles page. And so I created a Math Riddles page, which has been worked on very little bit, sadly, over the last couple of years when I was a grad student at Princeton. And this was the first problem that came on. One of my students asked me about this. There's a way to do this problem in one line. And to do this, we need the original classic Cookie Monster. So does everybody know who Cookie Monster is? From Sesame Street? What does the original classic Cookie Monster want to do? Eat cookies. Right. The new Cookie Monster is no longer always up for eating cookies. The original classic Cookie Monster is. So I call this the cookie problem. It's also called the stars and bars. So let's imagine C equals 10 and P equals 5. So I'm going to look at C plus P minus 1, which is 14 cookies. And Cookie Monster is going to come and eat 4 cookies. If there are 14 cookies and he eats 4 cookies, 10 cookies are left. And what's great about this is if you look at this 2, 0, 3, 3, 2, we have divided the 10 remaining cookies into 5 sets. This goes to A, B, it's not your lucky day, C, D, and D. There's a one-to-one correspondence with the number of ways Cookie Monster can eat 4 cookies from 14 as there are to divide 10 cookies among 5 people. How many ways can Cookie Monster eat 4 cookies from 14? 14 choose 4. And I've done this problem so many times, I know that 14 choose 4 is 1001. So rather than doing that long, tedious, painful calculation, I can get it in one line. Now, you have been trained with a sense of justice. Something should bother you here. What bothers you? You should not think this is fair. I know this is a math class, but this should bother you. Nobody's bothered by any of this? B gets no cookies, right? So what we've really done is we've solved x1 plus x2 plus x3 plus x4 plus x5 equals 10. Each xi is a non-negative integer. Solution, or the number of solutions, is 14, choose 4. In general, we would be solving x1 up to xp equals c, and the number of solutions is c plus p minus 1, choose p minus 1. If you want everybody to have at least one cookie, if everyone must get at least one cookie, you could let xk equal yk plus 1. And that reduces now to y1 plus yp. And how many cookies are now left to distribute? Oh, sorry, how many cookies are left to distribute? It's not C. How many cookies are left? Everybody has to get at least one. C minus P. Because all the x's are one more than the y's. So if the sum of the x's is C, then the sum of the y's is C minus P. So we've reduced this to a simpler cookie problem. And so the number of solutions is C minus P plus P minus 1, choose P minus 1. And then I'll do one last one. What if you don't have to distribute all the cookies? So then it's going to be the sum, little c goes from 0 to big C, of C plus P minus 1, choose P minus 1. Okay. This is a binomial sum to evaluate. Good luck. I claim you can solve this in one line. And we've still got like a few seconds left. So it's going to be C plus P plus 1 minus 1, choose P plus 1 minus 1. So the way you solve this is if you don't distribute all the cookies, that means you have some cookies left over, right? I know you often give apples to professors. Professors also like cookies. Give the extra cookies to the professor. So when you're trying to distribute at most capital C cookies, well, if you don't distribute some of the cookies, it's like you have an extra person who gets the leftover slack. It's just the original cookie problem now with one more person. So I've done a lot of research with students over the years where we've used this observation to prove a number of remarkable theorems. It's amazing the powers of these observations. What is really sad is we only know ways to handle at least everybody gets at least one cookie, or person I gets at least I cookies. We can handle stuff like that. We can't handle upper bounds easily. We can't handle nobody gets more than 5 cookies. We can only do that with painful inclusion-exclusion. All right, so this is a good place to stop. And then on Tuesday, we will start doing PDFs and CDFs. This will end the unit on combinatorics. It's important to just see a little bit of some of these basic calculations. And so if you do take a discrete math class or something like this now, you've now at least seen some of this stuff. All right.